Good afternoon or good morning, depending on what part of the country you're in. Today is March 29th, 2024, and this is the ASBI Lunchtime webinar. My name is Wade Bonzen. I'm the chair of the ASBI Construction Practices Work Group, and I will be filling in as your host, as well as running the Q&A session for today. Greg Freeby, who normally hosts these webinars, is unfortunately on the road traveling today, so we won't be able to join us. Today we've got a great presentation about the design and construction of the Chicago Transit Authority's first segmental bridge, and our presenters will be Kevin Bush and Ben Soule. But first, we want to make a few announcements and tell you about some upcoming events that are happening. First of all, these webinars are generally held monthly, usually on the last Wednesday of each month at noon Central Time. And registration is open on the ASBI website about a month in advance, so just sort of keep an eye out for those. And if you want to go back and look at recordings of past webinars, those are also available on the ASBI website. And also, ASBI has a YouTube channel. So if you search for ASBI Concrete Segmental Bridges on YouTube, you should be able to find that. Watching past recordings obviously won't count for PDH credits, but there's some great information about some really cool projects and topics on those. Just a reminder, the next monthly webinar is actually going to be on Tuesday, June 25th, so not Wednesday as it's normally held. And the reason for that is because that same week, we are doing the ASBI Construction Practices Seminar. So we're going to move next month's webinar to Tuesday, June 25th, noon Central Time. And we've got a great speaker, Matt Carter from Arup, is going to talk about the vessel collision studies and the lessons learned from those for the Queens Ferry crossing. So nice international project for the US folks on the line, and that'll be a really interesting topic that Matt's going to present. So please join us for that. And as I mentioned, the Construction Practices Seminar is going to be that same week. It'll be Thursday and Friday, June 27th and 28th. It's being held at the Spring Hill Suites by Marriott near downtown Denver. And you're more than welcome to register and attend this. We would encourage everybody to consider doing that. It's going to be a great, about a 1.5 day long seminar. You typically would fly in Wednesday evening, and then we'll have a half-day session on Friday that allows you to fly back out by the end of the day Friday. Registration's open at the ASBI website, so please join us. Also, the 2024 convention for ASBI, as well as committee meetings, is going to occur in October. Looks like about the third week of October, the 20th through the 23rd. And that's going to be held in downtown Atlanta, Georgia at the Lowe's Atlanta Hotel. So again, registration is open and available on the ASBI website. And as chair of the Construction Practices Committee, I do have to put a little plug in for the publication that our committee is in charge of maintaining and updating. It's the Construction Practices Handbook. That's a free download from the ASBI website. So go to the ASBI web address and then go to the Learn tab and look under Resources. The last edition was published in 2019, and our committee is currently working feverishly to update this handbook, and it's going to be a nice update. We're going to have all fresh, clean, new graphics and figures and lots of updates with current projects and that sort of thing. So be on the lookout for that. We'll probably publish kind of towards the end of 2024 at this point, although I can't promise a specific date at this point in time. But anyway, be on the lookout for that. In the meantime, you can download the 2019 edition as a free download. All right, just a few instructions for the webinar today. If you lose your connection, no problem, just rejoin the webinar. You'll just rejoin in progress. You can use the same link that you were provided to rejoin. You will miss whatever content that you didn't see while you're away, but again, you can always go back and look at the recording later. Certificates for attendance will only be issued to those meeting the minimum time required in the session. The way GoToWebinar works, it's advisable to keep the window that GoToWebinar has as the active window on your screen, which sometimes is a little tricky if you've got like a dual monitor setup. But you got to keep that window active on your screen to be able to count that time towards your attendance. So be careful with that. We'll send out attendance certificates, and those will be sent out about a week after today's session, and you'll see that arrive in your email. And then today we'll do a question and answer session here at the end of the presentation. Questions, we don't really have the ability to have people ask questions live on a mic, but we will just have you type in your questions. There is a question box, question dialog box on the GoToWebinar interface there. You can see here on the graphic where that is. You can click on that, enter your question, and we'll go through those questions here at the end of Kevin and Ben's presentation. If you are on a mobile device, the interface is a little bit different. There's a question mark in the upper right-hand corner, and you can click on that and then type in your question on your mobile device. This webinar meets the requirements of our CEP for continuing education. And like I said, you'll be receiving a certificate of completion about a week from now. All right, our speakers for today are Ben Soule. Ben graduated from the Massachusetts Institute of Technology, and he's got a master's degree in structural engineering from Cal Berkeley. Prior to joining IBT, where he is now, sister IBT, he worked at Jean Mueller International. At his core, Ben is a bridge engineer, and he focuses on specialty bridge design and construction engineering. He's got expertise in multiple concrete segmental bridges and cable-stayed bridges, and he's always looking for emphasizing ease of construction. Our other speaker is Kevin Bush. Kevin graduated from Purdue University in 2007 and worked for Flatiron Construction for a number of years, working on technically challenging projects on the East Coast of the United States. In 2013, Kevin joined Walsh Construction and has been working on some really interesting projects, the Ohio River Bridges in Louisville, Kentucky, actually both the downtown crossing and the East End crossing, as well as the Harrington Lake Bridge replacement in Harrodsburg, Kentucky. And currently, Kevin is the construction manager on the CTA Red Purple Modernization Line, Phase 1, and that's what we're going to be hearing about today. So at this point in time, I'm going to hand it over to our speakers, and we will hear their presentation. All right, Kevin, you should have control now.
All right, I am working on getting the right screen up. So just give me 1 second.
Yep, looks great.
Okay, looks good. Perfect. Thank you, sir. Okay, Ben, why don't you kick it off?
I will start with the introductions, and just to address the elephant in the room, that is a remarkably current headshot. I have aged incredibly well, so just keep that in mind. Picture that as you hear me go through this. So
Me
next
too.
slide. There we go. A couple of general purpose ones. The purpose and learning objectives here as part of our CEP. Design integration, advantages of precast segmental, and the challenges in a constricted urban environment. So keep that in mind. The next slide is just our CEP slide. And we're going to start with just a project overview, give you a little bit of context of what we're talking about and where. So, interesting. So the project is in Chicago. The client is CTA, the Chicago Transit Authority. And I don't remember, Kevin, I haven't done this. Show the system map if you click through. I think it shows a little close up and then a system map. There we go. So this is the system map of CTA's L system. So CTA operates all over and around the city of Chicago. It's a huge transit authority, 1.6 million rides on an average weekday. So lots and lots of people rely on the CTA to get them around town. And an important bullet point there is it provides around-the-clock service on certain routes. So that is true of where we are talking about on the red and purple line. 24 hours a day, 7 days a week, never stops. They also operate a bus system, but what we're going to talk about is a project as part of the L. So the elevated mass transit system, sort of the famous, if you've ever been to Chicago and been in downtown in the loop, the trains that are going overhead all the time. So almost 1,500 cars, 224 miles of track at 154 stations. Big operation, big part of the fabric of the city of Chicago. Next slide. And we are working in the red and purple modernization. So it's a section of the system on the north side of Chicago, affecting the red and purple, and in fact, the brown lines to some extent. Big undertaking that affects almost 10 miles of the red and purple lines. It includes all kinds of updates, both structural, that we're going to touch on more here today, as well as system upgrades along this corridor. So big project, the biggest capital project in CTA history to date. A lot of people putting their time and energy and effort into this. Next slide. So the two real areas of focus for structural changes, structural improvements. The first is the one that we're going to be talking about, the LBMM to the north there. It stands for Lawrence to Bryn Mawr Modernization. So it encompasses those 4 stations, Lawrence, Argyle, Berwyn, and Bryn Mawr. So it's on the north side, and it's about a 1.5 miles long of track that's getting redone there. We'll take a look at that in detail. The other part, and we'll just talk about it briefly, is to the south, the RPB section. And there's a quick slide on that. The next slide. So this is a good view of the RPB, just to give credit to everyone that's worked on that and our colleagues. So 2 big components to this. There's the bypass, and you can see the old and the new side by side there. You can see how 2 of the tracks cut across the other tracks that are heading straight north. And in the past, they did it in the same grade. So every time a train was going to the brown line, which takes you to the left of this picture, traffic on the red and purple lines had to stop and wait. So the bypass that you see there goes over the top. That was designed by our colleagues at EXP. And then everything to the north of there was in fact also reconstructed. This picture was before that happened. And that was all designed by Stantec, who was also the lead engineer for the entire project. Too many people to mention that contributed to this project, but those are some of the major parts and pieces of the structures there. So diving into our area, next slide. So LBMM, this is the area that we're going to focus on here today. The alignment over to the right, and the first thing you notice about the alignment is that it's really not much of an alignment. It's pretty much straight as an arrow there. It is by far the simplest grade and alignment I have ever worked on. Very slight grades, 1% kind of undulating up and down, station to station. I think one curve at the north end that was somewhere in the 1,000+ radius. So, very simple alignment, and that was an important part of some of the decisions we made. Over to the left, you can sort of see the story of what's going on here. So this part of the L system, there are 4 tracks. The red and purple lines are running on top of each other. So to the right, on the east side, are the northbound tracks. To the left are 2 southbound tracks. And in broad strokes, you can think of the inner tracks as the local train. That's the red line that stops at every station. The outer tracks are the purple line. Those only stop at a few stations, and then once they get further north, provide service to the northern suburbs up there. The original construction was on the embankment that you see there in the section. So it was an embankment with concrete retaining walls. That's been in service for about 100 years. It is getting replaced by a viaduct structure. So the alignment is moving up, as you can see here. It's actually getting widened out a little bit, so more space in between the tracks, and replaced with a modern viaduct structure. So the old is the embankment, the new are the 2 segmental box girders you see there in section. The next slide shows that in one location we have a pocket track. This is on the order of 1,000 feet long. So a 5th track running down the middle with connections to the tracks on either side. So you can use it for train storage, reverse direction, that kind of thing. And what we did to accommodate that track was a third box girder in between the typical two, connected with casting place closure pores on either side. Looks a little lopsided, and that had to do with the space available to the staging, for our staging. So those are the basic building blocks. And next slide here. And this is a picture of where we are working. So on the left, I told you it was about 100 years old. It has been around for a while, and the city of Chicago has grown up right around this. In some cases, grown up right next to it. So to the right, you see what it looked like. This is the embankment, so this is before construction. And in fact, you may see some construction pictures that Kevin shows later on, working in exactly this area. But you can see just exactly how tight of a corridor we are working with here. The buildings are, really arm's reach to the right of way in a lot of places. So very tight, very congested corridor. You're in the middle of a very urban environment, lots of people, lots of traffic, lots of things, neighbors to consider during construction of this project. Next slide. So the project was, if you've ever been to Chicago and had a look around, the structure you see to the left will be very familiar. This is sort of the classic, what you would see downtown, old style steel structure, stringers, so steel beams directly below where the tracks are, timber ties up above, and old school construction riveted steel. That's the Chicago way. They do a lot of steel, and what they had envisioned was a more modern steel structure like you see on the right. So welded plate girders, concrete columns, concrete deck. So you hear open and closed deck sometimes in Chicago. Open are the timber ties that you see around downtown. Closed is a concrete deck. You hear those words being used. So that's what was originally envisioned, is kind of the conversion to what you see on the right. Next slide. So our team took a look at that, took a look at the schedule, the cost, and proposed an ATC to change that steel structure to precast segmental. So what you see on the right there is a rendering, meeting all the same profile, all the same performance, and so forth. But it had a lot of advantages. It had advantages in that the spans were longer. A huge amount of the construction activity was pushed off-site into the precast yard. So again, being a good neighbor, Segmental had a lot of good advantages there. And of course, low maintenance. You're not in there scraping paint off and looking for corrosion. So ultimately, that was accepted. That's what we progressed with, that ATC on Segmental. And next slide. Kind of the other thing to talk about for context is the staging. We're very fortunate that we have 4 tracks to work with. That means we can close 2, do some work, close the other 2, and that's exactly what we're doing. So to orient you a little bit, in stage A, the eastern tracks, the 2 original northbound tracks are closed. The ones to the west are swapped over to 1 in each direction. We build the box girder on the east side. We then switch traffic once everything is assembled over there. So all the trains are running north and south on the east side. That's where we stand today. And erection starts on the west side. That is stage B. So just a little context for some of the terminology you're likely to hear. All right, next slide. So this is the part I'm actually supposed to talk about, which is the construction engineering. So we were both designer of the superstructure and the construction engineer for this. And to sort of orient you in what that task involved, we had a very simple bridge. This is the basic building block that we were using, 120-foot simple span, external tendons. So we didn't really have anything other than simple spans. We did have some variation in the span length, which we achieved. We used 120, 110, and 100-foot spans. The only difference is we took out the kind of the boring segments there in the middle to give us those different spans. Everything on the alignment is one of those 3 things, a simple span of one of those 3 lengths. So a very simple structure, very repetitive structure. I mean, that's exactly what you want out of a project like this. Do a simple thing and do it over and over and over. But on the next slide, for a construction engineer, that leaves you without a whole lot to think about. Simple spans, they're called simple for a reason, pretty easy to analyze, pretty easy to figure out. We do have some pretty heavy loads. We are storing segments on the deck. We are using a segment transporter to bring them along the alignment in It's a congested area. We have to use the alignment for a lot of the delivery. And of course, there's the truss, but those are fairly easy to analyze. The only thing that really is at all tricky and takes a lot of coordination with the contractor team is the transverse positioning of some of these big loads. Those wheels were pretty well prescribed to where they could be, and we had special cases, maybe where we had openings or an opening for a stairwell at a station or something like that, where it took a little bit of care and engineering to get through. So there you go. That's the construction engineering. Now, so if we weren't spending a lot of time analyzing a complex structure, what did Kevin give us all this money for? That's a good question. He's probably wondering that right now. Next slide. A lot of it was, oh, whoops. Sorry, I forgot that I wanted to talk about the gantry a little bit. So this gantry, if you look at it, is probably, looks a little unusual. You're used to seeing something with a bit of a wider base, maybe some articulation or something. But this gantry was really custom designed and created for this project. Deal is the gantry supplier. And you can see there's a single box beam that supports everything. Most of the time you're used to seeing two. And we have this sort of outrigger configuration for the legs. We could do this because of the alignment. So because we really have no curvature to deal with, the gantry could be simplified. It doesn't have to navigate tight curves. It doesn't require any kind of articulation. It doesn't really have to lift a lot of segments at an eccentricity. So it could be a very, very efficient truss. And we were lucky in that we had a partner that was willing to do that, and that the resulting loads were a little bit lighter than what you would normally see for a gantry lid. Okay, so next slide. Okay, if I didn't spend my time doing calculations of structures, what did we do? Well, an awful lot of it was integration. So transit structures by their nature have a lot of stuff compared to roadways. And Chicago is probably exhibit A for that, in that it is a 100-plus-year-old legacy system. You are working with systems that have been developed over time. Some of them may have had their design origins decades ago. So there are a lot of things that you need to accommodate, from the signals that you can see here to the signaling system, to the switches to move you from one track to the other, to the third rail, to everything that powers that, to the communications. There are just lots and lots and lots of things that need to get incorporated in this structure. This is particularly true somewhere. This is a shot in downtown in the Loop, but at a crossover like this. The next slide. So all of those things, of course, need to be connected. So in addition to the stuff on top, lots of metal boxes, lots of things with electricity that as a structural engineer, I'm kind of afraid of, they all get connected. So there are cables running every which way, and those things need to be coordinated. So there's a big job both on the designer side of figuring out where everything goes, coordinating the locations of all the penetrations, all the supports, all the inserts that you need to hold these things up, making sure that cables aren't hitting each other, really planning out where all of this hardware goes, and making sure that all of the things that you need to load up the segment with, which is a lot of stuff on the segment, is planned out, coordinated, and well understood, well in advance of erecting it or putting in any of this conduit. So what does that end up with from a construction engineer's point of view? Is a good example is on the next page. So this is a map. This is one span. I wouldn't go so far as to say it was a typical span. This is a fairly congested area. This is in the vicinity of one of those switches. But there's a lot going on here. You can see that even the legend of all the different stuffs of what all these little circles and X's and squiggles and whatnot mean takes up half the page. There's a lot of stuff to incorporate on here, and all of it needs to be planned out, coordinated with the systems folks, with the track folks, and embedded into a segment, sometimes a year, 2 years ahead of when it might get erected and connected to all of this stuff. So the planning effort is a big effort. A lot of thought and a lot of communication has to go into how these things fit together and where they all go, but it really pays off. Kevin can speak to that, but we had very few calls from, say, the installers saying, hey, we don't have a sleeve, we don't have an insert. It came together fairly well. So It's a lot of effort. It's a lot of effort to get people to pay attention to it so far in advance, but absolutely worth it at the end of the day. And the next few slides kind of show you what it looks like. So this is the finished deck. They haven't started running trains yet, but you can see some of that hardware installed. Doesn't look that impressive in person. You can't really see, all the cabling and all the sleeves. It's covered up with the few pieces of equipment you have there, but it came together very well. And next slide, a big part of the construction engineer's job is integrating all of that stuff. So that's not just figuring out where the duct needs to be, it's also coming up with revised details. Where do you, if you have to cut a bar, what do you do? How do you show equivalence? And not just integrating all the systems things, but drainage. And you can see in that section A there, just above the webs, you've got the lifting equipment. So those are the bars and plates to lift the segment. So you've got construction items to coordinate with it. And then a little bit to the left of that, you see sort of a weird looking thing on the underside of the box girder top flange. That's part of the straight current system. So you've got lots and lots of things going on that need to be incorporated. Next slide shows you a little bit of the complications. So this was during installation. Looks a little bit messy, but you can see what it looks like as those cables are going in and finding homes for everything. Gives you a bit of a flavor of the complexity of the job of the cable installers to get all this stuff put together and the right cable going into the right slots. So that was a big part of it. The other thing that took a surprising amount of time, if we jump to the next slide, is rail installation. So I wouldn't say this is exactly a pet peeve of mine, but it is a pet concern. It's something that gets overlooked a lot by the structural engineer and the contractor and the rail installer, and it really shouldn't. In my career, I've gotten a lot of phone calls of projects around the world where they say, hey, why are the bearings sliding off? What's going on here? Almost always related to this. It does lead to real world problems and it deserves a lot of attention. So this is rail installation. And to understand the issues with rail installation, I'm going to take a brief detour to talk about rail structure interaction. So next slide. So most modern train systems use what's called continuously welded rail. So that means that the pieces of rail are laid out and welded together to create one long continuous piece of steel. When I say long, it can be several miles long. So what does that mean in practice? Well, it effectively doesn't move. So when the temperatures go up and down, it doesn't expand and contract. The rail just sits there, doesn't really move much. And instead of getting longer and shorter, it gets stresses. So the rail, say when it heats up, it wants to expand. It doesn't move, it's compressed. When it cools down, it does the opposite. It would like to shrink, it's restrained, so it develops a tension. The bridge, on the other hand, is doing the opposite. It is expanding and contracting. It has an expansion joint, in our case, every 120 feet. So you've got this long ribbon of steel that's not moving, that is connected to a big rigid piece of concrete that is moving. How do those work together? How do you manage that? Well, you manage it with what you see here, which are the fasteners. They are called slip fasteners. They do exactly that. So they restrain the movement of the bridge relative to the rail, however you care to think of it, up to a certain force. At that force, they slip. It's a manageable force. And your average everyday force that you can generate from this on simple spans, you have to consider it, but it's not that big of a deal. When it is a big deal is on the next slide, is when the rail terminates. So take a look at the next slide there, Kevin. So take a minute to drink this in. It is subtly different. You can see the fasteners that were in the previous one, they're in between, the black ones. And then the silver ones are rail anchors. So those hold the rail in a fixed position relative to the deck. And they transfer the entire force that gets built up into the rail into the structure. Completely different order of magnitude from the slip fastener. This is a force you really have to pay attention to. You have to make sure that you have a good load path to get it into your superstructure, to your substructure, and down into the ground. Completely different order of magnitude. Where do you find these? So next slide. You find them in really two types of places. Whenever you change structure type, so if you perhaps have a long span structure next to simple spans and a big expansion joint, a rail expansion joint. In particular, you have to have anchors near those to hold the rail steady. You will have it if you say change from a closed deck to a belted deck. And you especially have them where you have special track. So all of these crossover type track works, they need to be held stationary relative to the bridge, so you have rail anchors associated with them. So you've got these places where you have rail terminations that are important to think about. And you also have to think about how rails are installed. And I'm going to talk about that on the next slide here. So what's going on here? Well, talked about how the rail develops stresses as it, heats up and cools down. The rail feels different stresses. At some temperature, it has no stress, right? You're going through this cycle, and at some point it hits zero stress. That temperature is not an accident. That is an engineered and prescribed number. In our case, it was 85 degrees. So whenever it's 85 degrees out, nominally the rail should have no stress in it. So if you think about it, when you walk out onto the site holding a piece of rail and set it down, it has no stress in it. If it happens to be 85 degrees that day, super, attach it, perfect. That's exactly what you want. You have a no stress condition at the right temperature. So in a perfect world, we would erect all of the rail on a day when it's 85 degrees. We don't live in a perfect world. We live in Chicago. So most of the time it's colder than that. That means you're installing a rail when it's, say, 40 degrees on. That means you have to induce into the rail the stress that it ought to have at 45 degrees or at 40 degrees. You have to put a tension into it so that later on that year, when it warms up and it's 85 degrees, it goes to zero. That's what these guys are doing here. They have a piece of rail that is locked on either side. It's attached with all the fasteners, and they are literally pulling it to induce that stress, right? So they're pulling on the newly installed piece of rail. They set a gap in the rail at the right distance to stretch it out to match that stress, and then use this hydraulic puller, pull them together, do the weld, let go. So as you are installing rail, most of the time you are stressing the rail. You are inducing a force into the rail. And that's important to recognize because that force is a big force when it comes to transferring it down to the ground. So next slide. So I had talked about how rail anchors are big concentrated forces. The same is true with rail terminations. So where if you just kind of stop the rail without installing an anchor, sort of the end point, you still get that big force transfer. You get all the force in the rail transferring to the structure. It's a little bit spread out because it engages a bunch of fasteners, but it's still a big force that has to make its way to the ground. In particular, it has to make its way through the connection from the superstructure to the substructure. And a lot of times that's where the trouble is. If you're working with elastomeric bearings and say you have a gap for expansion or something like that, it'll close that gap. It'll pull the span over, it'll pull your bearings over, what have you. It may overload the shear capacity of a fixed bearing. It may overload a shear. It's something you have to know you're doing. It's something you have to pay attention to and watch out for. What we ended up with is this. So what are we looking at here? This is a map of the entire alignment. So the north end is in the bottom right, the south end is in the top left, and the different colors are the strings, the literal pieces of rail that Walsh was installing out there. So each color means a new piece. What we did was we worked with the rail installation team. We figured out comfortable places for them to stop work, to stop welding things, stop pulling things. Those are the yellow zones. Those areas were specifically designed for those forces. We blocked off the shear cues to prevent movement. We checked everything to make sure. In a couple of cases, we had to upsize a few things. And we had sort of safe zones where they could stop work. And we're going to do the exact same thing when we go through and install the rails on the other side. So message for everybody here, your rail installer is going to think you are crazy if you bring this up, but it's important. I've seen a lot of projects that get pulled off of the bearings, things like that, because this isn't being addressed. So rail installation, important deal. I'll hop off my soapbox now and hand the soapbox over to Kevin, who's going to talk a little bit about construction and the progress they've made.
Excellent. All right. Thank you very much, Ben. As he said, I'm going to talk through, there we go, some of the construction sequences. So for those of you who have seen us at ASBI, some of this goes back to the beginning of stage A, but I think it's worth sharing again. So I'm going to go through some of the construction in stage A and then leading up to where we're at right now. So in the beginning, the pictures that we've got on the screen right now, just putting the gantry together, and on the right you can see us working on the east alignment. So that'd be tracks 3 and 4. Like Ben said, we took those out of service for that 1.5 mile stretch, and then put the trains on tracks 1 and 2 on the left side of that picture. And then we erected that gantry right here on a small cross street called Ardmore Avenue, if you're looking on a map, using a 550-ton crane to get the structural elements in position. And then we actually used, go to the next one, some specialty equipment to get it moved into location. So we'll go into that in a couple minutes. But prior to the superstructure work beginning, in the beginning of the project, Ben alluded to the embankment that was supporting the existing tracks, and the original plan was for those embankment walls be cut back at the cross streets to create ramps, so we had access up on top. But at the end of the project, these embankment walls would stay in place just to serve more or less as fences for the area, but they don't serve any structural purpose for the bridge. The bridge is designed to obviously not require the existing retaining walls and embankment to support the structure. So in the beginning, you can see just our logistics and the site constraints. So we've got the excavator in the middle, the 2 left pictures, unloading the ballast and the embankment material into dump trucks that are lined up in the alley. And then moving out, and then at the end of our initial prep phase on each block, you can see the crane mats, and there's some pockets there where the future shafts will be installed. So this is how we build stage A from up above. Ben mentioned that 24/7, 365 days a year, trains are running. So we're not allowed to interrupt them necessarily, and we had to work to come up with solutions so that we could work next to the track. So on the far left, you can see the guys installing sheet piles on it's our stage line sheeting to separate the live tracks from the existing embankment. You can just see the proximity. So there's flaggers that you can't see in the picture, but once that train would pass, then we'd have a couple minutes to get that sheet in. And then if the next train was approaching, we might have to stop and wait for it to come through. And we proceeded for the 1.5 mile stretch along the alignment to be able to get that stage line sheeting installed. In order to install the drilled shafts, which were 2.2 meter shafts, so we used some temporary segmental casing just because of the existing structures, adjacent structures. We didn't want to cause any settlement, so everything was temporarily cased. And in the middle picture, you can see the size of the equipment, and in this case, the proximity of a 250-ton crane to the oscillator that's installing the segmental casing, and then you can see the drill towards the top. And then on the far right, it blends in a little bit, but you can see the rebar cage. We tripped it from the south side of that crane, swung it around 180 degrees to the hole, but you can see he's boomed up tight, and he's about 6 inches away from that temporary barrier that separates us from the trains. And he's also about 6 inches away from that building in the background there. So those were just day-to-day site constraints that we dealt with in the beginning in the stage A. Once drilled shafts were installed, we had pier caps that typically 6-foot columns, and then standardized pier caps. There's a couple different variations, but we pre-tied the rebar cages for the columns and the caps, and then we actually poured everything monolithically in one shot, including the bearing pedestals. In the middle picture, you can just see some of the congestion, the rebar with the shape that we ultimately selected in conjunction with the CTA and their preferences. It resulted in there's a lot of congestion with the rebar and all the hooks, and then you can see all the temporary PT bars and form savers for the shear keys in the middle that all have to be installed well, which the jigs work very well. Set the cage with all the temporary PT installed, and then pour it, and we've had great success with that operation. So going through the erection equipment, just high level, I know Ben spoke about it already, but we've got, I think what makes this job unique, and especially in stage A is the only option we had to get segments here were from the back, just because it's so tight and there's only a couple select cross streets that we can utilize to deliver the segments. We didn't really have the opportunity to get segments underneath the gantry where you can pull them right off the truck. So everything had to be delivered utilizing a transporter from behind. And that's also, the logic on that portal frame on a rear support. So you can get the segment from behind through the rear support and out to hang. Obviously, that's not the most efficient method. And ideally, if our site constraints were less than what we're actually dealing with, then we wouldn't be doing it like this. But it's a great solution given the circumstances. So now I'm going to go into a little bit more detail on the initial assembly of the gantry in stage A. So just going through the steps, we had temporary pier bracket up on the end pier. We had temporary false work across the street. And then you can see that 550-ton crane in the street setting the sections of the main girder, which the gantry is about 285 feet long, so 7 40-foot sections roughly. Once the main girder is assembled, which really just the main girder is assembled and then the winch underneath, then the next step was to actually bring Mammut in, and we supported the main girder, removed the false work, and then utilized SPMTs to relocate the 285-foot main girder to the south to get it onto the segmental spans, because on this particular cross street, we're transitioning and tying back into the existing alignment. So we didn't have the same depth availability. And so it's a steel superstructure, closed deck superstructure. Clearances are much less and the piers are much tighter space. So in order to be able to access the, have our crane in the main street, we could only reach so far to the south. So we had to build that main girder over the street and then relocate it with SPMTs. After we got the main girder in position along the alignment, you can see to the right of that first red tower, that's the transition pier that supports segmental on the left and then steel superstructure on the right. So once we got the main girder aligned with that, we transferred all the load to these 2 red towers, and then we installed the rear support and the front support, and then going forward, after that was complete, you can see on that left photo, the elevation of the gantry is relatively low to the ground. You can see the front support in the background there, and you can see how close the main girder is to that red gantry. In the middle, you can see once those red gantries are extended, we actually lifted it up, I don't know, 30 feet or so to get that rear support to clear that temporary pier bracket. And then let's see, I think it's in the next picture. I'm going to skip ahead one. Oh, I'm sorry, I'm going backwards. In the final step, once we lifted the main girder up to clear that pier cap, the Mammut gantries are actually on a tracking system. So we had to pull those gantries, travel them forward, and then land that rear support on top of that pier bracket. So now we have, the fully assembled gantry up on, I don't want to say flimsy, but pretty tight towers. We had very light wind requirements. We had a beautiful day and it worked out just fine. But transferred it, moved it longitudinally to the south, and then landed on the pier. And then at that point, once we anchored it down to the substructure, we were able to finish up the assembly and then start segmental erection. So just a couple pictures. Typical span erection. We got the segments come to the rear, and in this case, you can see the low boy in the street, and we picked that first span up directly with the winch, and then brought it through the rear support out to the main span, and then hang everything, get the deflection out of the truss, and then going backwards again, and then proceeding with the assembly of that span, and then launching to the next span. So a couple more pictures showing just site constraints again. So on the far left, you can see that low boy. He's actually backing in off of the main street. He's backing in underneath the existing viaduct that's in that picture was currently supporting train. trains and backs up to the crane. And then with the crane, the LTR that's also sandwiched in there in the block, you can see just tight quarters everywhere. Pick the segment up, land it up top, and then at that point, the transporter takes the segment and either stores it or brings it right to the gantry, depending on where we're at in erection. Switching over to the pocket track, Ben talked about this, but this is where we have crossovers between what would be tracks 2 and 3. They don't affect tracks 1 and 4, which are on the very outside, but the 2 tracks towards the middle in green, 2 and 3 connect to the middle track or the pocket track. As far as staging goes, north is right, and stage A is the first portion of the first stage of the segmental bridge assembly. And so the pocket track girders themselves were erected in the first stage. So right now, with trains running, these 2 boxes are constructed. And then pocket track, just erection, I guess, sequence consisted of typical span erection with the gantry. The pocket track segments were detailed slightly differently to accommodate the same spread on the lifting points. So we had a different, we just went right through the flange instead of into the web because the webs are a little bit narrower here. So we assembled the span with the gantry on the east alignment, so that gantry never side shifted. It was always on the east alignment. So we assembled the span, and then we had some low profile beams that we were able to set across between the 2 piers, and just using a simple strand jack and obviously some stainless and PTFE, so smooth sliding surface, pull that span right over, and then installed temporary jacks, lifted it up, pulled the beams out, and set it on shims, and then proceeded with erection of the east span in that same area. And through the pocket track area, like Ben was alluding to, and some of the snips he had from the model, it's quite congested here. There's a lot going on with the crossovers and subsequent just all the systems and signal equipment. So these couple shots are looking in that zone, in that pocket track area. On the left, you can see what's going to be an opening, and there's some big concrete blocks that are hanging to handle that eccentricity because that wing is clipped off from the east box to accommodate a temporary opening for what you can see in the third picture to get people up those stairs to the deck level to get onto the platform. And the middle picture is just, I thought, kind of funny. It's a 20-meter pump, but to be able to pour some of the temp station walls and footings that we have in the picture there, I mean, we had to work underneath the bridge and unfold that boom with almost no clearance at all, but that's just how it works here. It's quite tight. So a couple more pictures of the temporary station. The first one on the left is looking down, so you can see there's an opening that's currently in the box, one at each end of the platform. Eventually, in the final stage, which is stage C, we will disassemble the temporary station and then fill in these openings and complete the track through that section. But the other pictures on the right hand are just showing the integration of the temporary station and platform with the structure, both the substructure and the superstructure. So this is one of 2 temporary stations that's currently in service right now. And then the other temp station is the Bryn Mawr temp station. So this one, to me, is interesting from I guess more of a structural perspective, but it's a big can opener acting on the outside, the west flange of the box girder. So this temporary station is anchored directly to the box and fully supported by the box. So on the right, it's just a picture looking south. You can see what the customers are currently utilizing to jump on the trains at Bryn Mawr right now. And a couple other overviews. So segmental erection on the left with some other activities going on underneath. That's the Winona Relay Room construction. We had some union issues that led to quarry strikes in Chicago. So it forced us to get into a position where some of that work got delayed, and we were literally working over the top of each other, but we were able to get through it and work around each other to be able to work on that building and superstructure at the same time. But it was not easy, to say the least. In the middle, you can see the picture of the transporter and just the previous alignment, a little bit of curvature there, but very gradual. And then on the far right is prepping for some of those crossover pours in the pocket track area. So since stage A was completed, there's been a couple major developments. The first of which is at the far left, a picture of Walsh floor, and it's mainly CTA folks here, but with the 100-year-old wall in the background. And as Mr. Carter himself once said, Walsh floor, tear down that wall, but of course, hurry up. So late in stage A, after discussing what the final wall conditions would be with the CTA and just the fact that it's a 100-year-old wall, I think they became aware and on board with the fact that it's, instead of repairing the wall just to keep it there, it's probably smarter for everybody to get rid of it. So they did direct us to take the wall out. So you can see in the middle picture, that's just once we've excavated a lot of the embankment, you can see some of the existing wall. This is a cellular wall on the west side, typically, and then a gravity wall on the east side, typically. But that's what it looks like after we removed a lot of it. And then on the far right is a picture standing up at the north end looking south, but just seeing, you can see the crane and the drill, and it's a night and day difference from construction perspective to be able to work at grade instead of up on top of that embankment, which was the original intent. So it's been we've welcomed the change. And then just continuing through here on the left side, we can see some of the substructure. And one thing that I love to see is there's a mile of substructure, which means the gantry is not going to get slowed down by anything that needs to support it. So we are in the process right now, actually crossing over one of the main streets, Bryn Mawr, and then a week after next, we'll turn into double shift and start accelerating the superstructure to get down to the south end. And on the right-hand side, it's a picture of the Bryn Mawr stations. You can see the temporary platform up above. You can see the east box that was erected in stage A that currently has trains running on it. And you can see the escalator truss installed. And then the gantry is not far away from here. In this photo, on the top left, that's the existing infrastructure. And Ben alluded to this one as well, but the base case had roughly 60-foot steel spans, which would end up with what I would call the typical layout in Chicago. And you can see there's a center pier dividing the traffic, and then there's typically another bent on both sidewalks. So just from an access perspective, it's quite congested. On the bottom right, you can see this is Hollywood. You can see both of the boxes now erected over the street. And you can see the piers are pretty far offset from the street, and there's still a lot of work to do underneath. But at the end of the day, it opens it up significantly, and it will just create a better condition for everybody that's passing through, whether it's driving or on the sidewalk. And then current progress, like I mentioned, we're over Bryn Mawr, which is the street that's shown in the picture right now. So I wanted to kind of highlight just how close everything is together. And then now that we're this far along in the project, seeing the east box erected, that steel platform in the middle, which has been erected, and then on the left side, the gantry and the segmental bridge coming through. Once the west box is built, then we can continue on that platform, the precast that goes up on top of the platform, that will ultimately service both tracks 2 on the west bridge and 3 on the east bridge. So with that, I'm gonna ask if there's any questions. Thank you all very much, and I think the next year or two, as construction proceeds, we'll have more to share. Especially as we get next May is when we'll be opening up the west box to train traffic, and then just getting into the finishing works. So again, thank you all very much. And Wade, I'm gonna defer to you. Would you like me to read questions if there are any?
No, we've got a bunch of questions. I'll just start firing them at you here. So let's get started. Okay, Kevin, this one's a question for you. I'm going to read it word for word because I'm not sure I understand it. Why was the gantry not installed using the steel spans like stage B? And which was cheaper, installing the gantry using the steel spans or using the 550-ton gantry? I think it means crane.
Yep. Yeah, no, that's a wonderful question. Sounds like that person is relatively familiar with the job. So in stage A, early on, we made the decision to forego the erection of the steel girder bridge because in order to be running the bidirectional traffic on tracks 1 and 2, there was a lot of signal infrastructure upgrades that were required to be complete. So just, you know, the trains hadn't run backwards on those tracks before. So in order to prepare for stage A, we got ourselves into a situation where there was still a lot of signal work. So without delaying the entire project, we decided to push off the closed deck, steel erection at the north end, build the gantry utilizing that 550-ton crane at Mammoth. And then once segmental had proceeded far enough down the alignment, we could come back in and install the closed deck bridge at the north end without impacting the critical path. So in stage B, we did the opposite. We built the steel girder bridge, like one would imagine, and then we built the gantry. And you know, the crews, we had a lot of the same people involved in the operation the second time around, but from a cost perspective, night and day difference, much more efficient, safer, just overall, you know, way better plan. And I would, you know, not want to do what we did ever again, but it did solve the schedule problem that was presented to us that we got ourselves into. So that's kind of the logic.
Great. Okay, thanks. Couple questions about the precasting operations. You guys didn't really touch on it much in this presentation, but I know that you all have done some interesting things during segment precasting. Do you want to talk a little bit about the benefits of some of the prefabricated wire mesh cages and some of the special concrete mixes that y'all were using?
Yeah, I mean, without giving away too many secrets from our precaster, I think they were, you know, they brought to the table early on. I mean, really before the design even started, they brought to the table both high slump concrete mixes and prefabricated wire mesh. And so I think working with Ben, it took a little bit of time to get everybody comfortable with that and just, well, yeah, get a compliant design mainly on the rebar side. But we were ultimately able to get that approved. And then I would say our precaster UCP worked with Deal, who supplied the erection equipment and also the casting equipment, but worked with them as far as supporting the you know, the full liquid head on the self-consolidating concrete. But you know, by employing both of those items, I think our precaster is able to save time, money, and ultimately the finish on the segments looks great. So at the end of the day, I think it's just a huge benefit for all involved.
Yeah, and Kevin, I'll add a little bit to that. It did take a little getting used to on the design side. The switch to mesh, that is, not terribly common, and spent some time, you know, ourselves and working with all of our partners and the owner, going through and making sure we were comfortable with the details we were using. It wasn't used uniformly. You know, we were paying attention to the literature and the practice that was out there, but you know, eventually made good use of it. The other thing that I would say though is that is a real advantage in transit in that you know, transit, you're always worried about stray current, so you're trying to collect all the metallic pieces so you don't have things that are just kind of left out there to corrode. And welded wire mesh is good for that, right? It comes automatically welded, as opposed to using just regular rebar where you have to assemble it all and then go to the trouble of tack welding a bunch of them together. So you sort of get that, I want to say for free, but automatically.
Great, thank you. Another question about the casting. Did they use the same casting cell but modify it for that smaller pocket track girder, or was that a whole separate casting cell?
No, that was the same one. They were able to modify it for the pocket track. So I guess among other things, we had to take into consideration long-term effects. And so the way that, I mean, we worked together, ultimately come up with a schedule where we started casting stage A, typical boxes, and then we got to a point where it made sense for our precaster to switch to the pocket track and cast that entire alignment, and then switch back to the standard forms for the west box. So both to help, I guess, from an efficiency standpoint, it helped them, and then from a long-term effects standpoint, it helped Ben and us.
Yeah.
So go ahead.
Those long-term effects are related to trying to understand how the different boxes are going to creep in the pocket track area when it's time to join them together. And another fun thing with the forms there, the stage A, the boxes that are already erected, due to various constraints, we had to sort of vary where the tracks were relative to the webs. You know, we had the one sort of clearance of where we could put columns, and sort of had to cantilever out over the alley on the east side sometimes. So Dio, who was supplying the forms, worked with us to basically shift the entire top flange, so that the shape, all of it just kind of shifted one way or the other so that we could put the tracks at offsets that I can't remember what we got up to, Kevin. Do you know? It was over a foot.
I think it's about 1.5 feet.
Yeah.
1.7 feet maybe.
Which, you know, it would sway in and out depending on our constraints and our geometry. So a real nice job by the precaster and getting all of those right effectively, the subtle changes in geometry.
Yeah, and I guess just to piggyback on that aspect of it, we had some pretty tight requirements in the alley to maintain clearances mainly for garbage trucks that are coming through and have their minimum alley widths. And so to Ben's point, that top flange was offset from the webs up to about 19 inches. So there was in the stage A side, which was the first, the east alignment, the first segments that were cast, UCP had to alter for a lot of the alignment, almost every segment by a small amount to cheat it over to keep that, keep that flange offset properly. So small details that affected both casting, and then obviously the rebar had to change slightly at every segment, every span.
Yep.
Yeah, interesting. Yeah, a lot to think about. How many spans were there for the pocket track spans?
11.
So
So the west and east boxes, there's 63 spans each, and then 11 additional in the pocket track.
Got it. Okay. Let's talk a little bit about the rail tension and all of those issues. I guess that's probably a question for Ben. Does the long-term creep, shrinkage, and steel relaxation in the precast segmental box girders, does that actually have an appreciable effect on the rail tension forces?
Pull back the curtain. I wish I knew. You know, and I have to be honest about what the industry does and doesn't know about this. You know, we know that the boxes move back and forth relative to the rails, and that can cause, you know, its own set of stresses in the rail that get added to the temperature effects. But we're not great at really understanding, call it the hysteretics of that. You know, that all of the modeling shows that, you know, you start at a neutral temperature, you go up to 120 degrees, or you go down to, you know, whatever you get in Chicago, -1 million or something. And you model these discrete cases, but nobody ever goes through the hysteretics of, you know, today it's up to 85 and it cools off to 60, and then it's 90, and then it's even 55 and back and forth. And creep very much falls into that category, right? How do these things develop over time? How do they dissipate over time? There's a lot of thought out there, if you look through the literature, that, you know, even if you ramped up to 120 degrees and just held it there, the forces eventually leave the rail. You know, as the trains go over and it vibrates slightly, the forces from the clips dissipate. But, you know, boy, if somebody's got money to burn on a research project, this would be a good gap in the industry's knowledge to fill in. Just to directly answer the question, though, we usually err on the side of conservatism and include creep and shrinkage effects in the rail structure calculations, but not always. If the owners feels confident in leaving it out, they may. But yeah, since we don't know, we try to err on the side of conservatism there.
Interesting. Similar question. I'd assume that you would have the same kinds of rail structure interaction issues even if the superstructure was steel.
Oh, absolutely, absolutely. You know, the rail structure interaction happens when you have a rail that doesn't move that's attached to any kind of structure that does. The stuff that's specific to guideways anyway. You even have it when it's, you know, just on the ground on ballast track. A different set of problems, but you have, you know, things to think about on those. doesn't matter what structure type it is. Really what matters is the distance between expansion joints. When you have very long structures, the rail stresses that are induced by these fasteners can get too big, and you have to introduce a rail expansion joint. But you know, the kinds of things you do for segmental viaduct or any other viaduct, 120-foot spans, even 200-ish foot frames, you really don't need to do anything particularly special. When you move outside of that, that's when you start needing to do something fancy.
Yeah, so do you think there was any, the fact that you all had a concrete structure that was already, post-tensioned and pre-stressed and whatnot, do you think that provided any inherent advantages to handle these rail interaction forces?
Yeah, I mean, it's you could make the argument, and it depends on what you think about temperature ranges and structure materials. ASBI may give you different temperature ranges for different structure types. And in this case, by code, concrete was actually an advantage because the temperature range was not the same. It was smaller than steel. I'm sure opinions vary about is that actually true in practice or not, but it may vary by code. But that's really where it would show up is a real or perceived difference in the temperature range you should design different structures for.
Got it. Okay. All right. Some cost and schedule questions. What was the weight and cost of the gantry?
I want to say 600 kips, rough numbers, right, Ben? Does that sound right?
Man, it has been so long. I don't remember if it was 600 kips or tons.
It's definitely not tons. Yeah, I think it's around 600 kips for this one. And again, we had the single box. So yeah, this one's about 600 kips, and cost was the couple $1 million range, but through specialty segmental equipment suppliers, manufacturers.
Yeah. Okay. And then how long did it take to actually install and make the erection gantry ready to operate?
In the first stage, without having an old schedule, I would say 3 months versus like a month and a half on the second stage. And we also, the timing of the year, but in both stages really was not ideal. But in stage B, our current stage, erection occurred into the winter. So is right after the winter, I guess, so that segmental assembly erection can start immediately following the winter. So that part timed out very well. So we're starting out in the summer, or in the springtime with segmental erection, trying to finish before the winter comes.
Okay, great. Yeah, it's amazing what you can do once you get over that initial learning curve. And the first time you do something, it always takes much longer, but after that, you can go much faster.
Yeah.
On those same, in that same vein, how long did it take to erect and post-tension each span of segments?
So on average, I'm just going to say a 4-day cycle for start to finish, including the launch, and that includes weather. So sometimes, obviously, we can beat that, but overall, it's up at the 4-day per span duration.
Okay, yeah, not too bad considering the tight constraints and the difficulty of getting segments in there. So that's pretty good. All right, a couple random questions here, just not in any particular category. The sheet piling that y'all used out there, was that installed with zero vibration methods?
No, we used an ABI almost, I think, everywhere and vibrated them in. But they went in very easily.
Okay. And was there any consideration given to utilizing the gantry similar to some of the other projects we've seen in recent years, where the gantry at the front end has some pile driving equipment on it, leads and a hammer, in lieu of doing drilled shafts?
So I guess I can start this and Ben could probably finish it, but speaking about the sheets and asking if we were vibrating them in, I guess one thing I should add, so we had a pretty robust monitoring system set up on the active tracks, so we can monitor any settlement in the rails while we're installing the sheets. So we're constantly monitoring those during installation. But to answer your question about having a different gantry that maybe was driving pile, the technical requirements precluded driven pile. And I think from the vibration settlement perspective and concern of the client with the existing structures, both their own and adjacent buildings that were right next to the, where the new structure is going in. Ben, you may have more to add to that.
Yeah,
Well.
and you're exactly right that we couldn't use driven piles, part of which is the settlements and the active tracks, but also just the environment, very noisy. And I would guess that the schedule wouldn't have been right for that. You do have downtime in Chicago where it's not a great idea to erect when it's cold, so you want to really use that superstructure erection time to best advantage and not add another thing to the cycle.
Yeah, that's all.
Actually,
That's a good point.
I'm glad you brought that up, Ben, because that's the next question here. That temporary condition where there was only a single track pair while you're constructing the other side, did that result in a lesser than normal train service? And as a result, was there like a time limit in the RFP for how long that particular condition could exist?
Well, to be clear, I mean, we maintained north and south tracks, so there were 2 tracks operational all the time.
Right.
I don't want to get too far out on a limb, but it doesn't take much imagination to think that especially the purple line, which is more of the express, probably did have some disruption to service in the sense that it just took longer to get through the stations and had to wait for trains that were stopped. Probably not that bad because there were only 2 stations operational, where typically there were 4. But I'm really way over my skis. I don't want anyone to take this as gospel. But there was north-south traffic maintained more or less the entire time.
But was there a time limit for that temporary condition in the RFP? Like, did that play into your selection of structure type?
I don't know if it was really so much related to operations like that in terms of having delays or mitigating that. Just that as it was, the overall schedule really would have swamped that. The priority on the overall schedule kind of would wrap that up. And that was where segmental really shone. There were several months taken out of the schedule from wash floors estimating on it in the bid phases. Segmental was seen as a clear advantage when it came to the schedule.
Fantastic. Well, I really appreciate it, guys. Great presentation. We're bumping up on about 1:15 p.m. Central Time now, so I think we're going to call it good for today. And thank you so much for presenting, and I hope everybody enjoyed today's webinar. And we will see you next month.
Thanks a lot, everybody. Have a great day.
Bye-bye, everyone.